just a re-recording of the lecture that I'm going to wind up having given twice yet again. Okay, so topic for today's lecture is force balance. So what do I mean by that? And torque balance. So these are situations where we have a static system of, blocks, a board on planks on top of each other, a ladder up against the wall. So it's static. And what do we mean by static? Nothing's moving. So because nothing's moving, so if I take any individual component in whatever my ensemble is, the sum of all the forces on that object all sum to zero, because if they didn't sum to zero, there would be an acceleration and it would start to move. And also all the sum of all the torques on every object in the ensemble have to be zero. Otherwise, things would start to rotate. So another way of describing this situation is equilibrium. So all the forces cancel out, so things don't move. These conditions don't tell you if the equilibrium is stable necessarily, and we'll talk about that in the middle of this lecture. So I'm going to redo some of the problems that I started doing in lecture on Thursday. And that's because I want to be very clear about how to calculate the signs for the torques. And so here's the problem. The first problem we're going to do is we've got a scale here. And we've got a scale here. And there's a board. But I'm going to make it just so the edges are really essentially at the ends of the scale. And the board has a mass, little m, and gravity is exerted in the middle because the board is uniform density. And then I'm going to put a weight on top of the board. And this has mass big M, and so it's exerting a weight mg on the board. And then we'll put the position of this L over 4 from the end. The distance to the center mass will be L over 2, and the length of the board will be L, just L. Okay, that's the length of the board. So I have these scales. So there's some upwards force exerted. The scales, there's weight on the scale. So there's an upward normal force. So we'll call this one FR because it's the right side. And we'll call this one FL. So these are upwards on the board. So, so in order to keep track of signs here, when I'm computing torques, it's handy to define a coordinate system. And so I'm going to pick a coordinate system that looks like this. And if I want the Z, it'll be in that direction. So I'm going to take up to be Y, just, just convenient coordinate system for things, right-handed things. Okay, so so in this case, we'll do force balance first, and then we'll do torque balance. So sum up all the forces. So on this, all the forces are in the vertical direction. So we have Fy, and so there's a downwards force from the block, and we have a downwards force from the center of mass. Downwards force on the board from gravity. We don't worry about where it's exerted yet because we're not computing torque. Then we have these two upward forces. And since everything is in balance, this is zero. So that's our first condition. So let's break this at the top. FL equals M plus mg. We'll just remember that condition. And now let's compute the torques. So so you could compute the torque either here or here, and they're gonna give you slightly different conditions, but I suppose, what are we trying to, before I start computing torque, let's ask what do we want to do? So what's our goal? Find FR and FL. So our goal is to predict the what's measured on the scales. And find it. That's our goal. So we assume we know M and big M and little m and G. And so we have two unknowns. And so right now this vertical force balance equation, we have two unknowns and a bunch of known things on the right side. So we need one more equation to find, one more equation. When we have two equations with two unknowns, we can find both of them. So we only need one more equation. So we could either compute the torque here or you can compute the torque there on the board. It doesn't really matter because we can relate them. So I'm going to compute the torque around this position. So torque computed around on the left-hand side. So this is a vector. So I need, in order to do R cross F, so this will be R to this mass. So the length of it is L over 4, and it's in the X direction. So we'll put X hat. And now F is in the downward direction. So that's mg, and it's a minus sign because it's down with the Y hat. And now I have to do the same thing for the center mass. So this is going to be L over 2 X hat cross minus mg Y hat. Like this. And then I have, so now what about the upward forces from the scale? So the one on the left here, the distance to it is 0. So I'm assuming the edge of the board is really close to right on the scale. So R is, so the radial vector to that pivot point is 0. So this force doesn't give you any torque, but this force does. So FR, so if the distance to it is L, it's in the X direction, and then the vertical force cross FR Y hat is upward. So I can rewrite this, and so now X hat cross Y hat is Z hat. So it's minus L mg over 4, and this is minus mg L over 2, and plus L FR, and it's all in the Z hat direction. So yeah, that's right. So we can get rid of let's see, we can solve for this. So we can solve for it. Let's solve for it. So FR is equal to, this has to be 0 for torque balance, right? So now we can solve for FR, and the L's should all cancel out. So we have M over 4 plus M over 2 times G, and I think that's it. Yeah, that is it. Good. So we have FR, and now once I know FR, so that's half of the things we wanted to find. Now I can stick FR in this and solve for FL. And if I do that, you get this 3M over 4 plus 1/2 with a little m times G. Yeah, and so that gives us the second part of the thing that we wanted to find. Okay, so the whole point of this exercise was to show you how I kept track of all the vector components here so that you wouldn't make any mistakes when you try and compute the torque direction. So you can do that in various ways. You can figure out the sign. So in this particular case, torque is in the z direction, but you just have to be consistent about whether it's this way or that way. And so one way to make sure that you get the signs correct is to write down the vectors all with respect to some particular coordinate system, and then use the fact that you know x cross y, x hat cross y hat, z hat, etc., to get the signs right. So that's what the whole point of this problem is to do that, to show you how to do that. Okay, so let's move on to the next example. Next example. Okay, so the problem is a ladder. So first I need the ladder on a wall. So here we have a wall. So this is a wall. And there's the ground. Ground. Let's use different. Then we have a ladder here. And that's a ladder. Ladder. And there's an important point there. Okay, so now I need to draw a guy walking up the ladder. So I'm going to draw him right here. So let's put his head here and make him look like an XCD guy. And here we have his foot like this. And he's walking up the ladder. And he's got mass M. Mass M. And I'm going to put him halfway up the ladder. And that's A, distance A. And we'll take this distance here to be H. That's the height of the ladder up against the wall. And now we need a center mass. We need to worry about, so this is mg. mg here. Then let's take the center mass of the ladder here. So m mass of ladder. And we're going to assume that the center mass of the ladder is A over 3. A over 3 away from the end of the ladder. Let's draw that a little bit more carefully. Let's do, take it down here. This is A over 3, like that. Okay, so now that's good. What are we trying to do? So what are our goals? Goal. Find the friction force. When does the ladder slip? So that's the goal of this calculation. So this calculation is a little bit more interesting compared to the previous one, because the previous one we really only had vertical forces, but this one we have both vertical and horizontal forces, and so we have more things to compute. So when does the ladder slip? So the interesting point is here. So there's the force from the ground on the ladder we can describe in terms of two components, so I'm going to use the subscript G to be ground, because it's the force from the ground exerted on the ladder right at that point. So there's a normal component, it's normal to the ground. And then there's a horizontal component that's due to friction. So this is the friction. So if the friction is large enough, then the ladder doesn't slip. But if you remember from the static, or the Coulomb law for static friction can be at most some friction coefficient times the normal force. And so the maximum size of the friction force is friction coefficient times this thing. And so the ratio of these two things required to keep the ladder from slipping gives us, is either allowed, meaning this thing is low, the required value of this is low enough that it's below the critical one, and that means the ladder doesn't slip, or it exceeds it and then the ladder slips. And so I remember when I was walking up the ladder in the demonstration on Thursday, at some point it started to slip, and so we'll find out when we do this calculation that the distance of the guy climbing the ladder up the ladder increases the required value of the friction coefficient to keep it from slipping. And at some point it gets exceeded and then the ladder slipped. That's what happened in the demonstration. Okay, so I've written down the vectors for the friction and the ground normal force. So there's a wall force, and we're going to ignore the friction component just to make this problem a little bit easier. So there's a wall normal force also exerted on the ladder. Okay, so now let's do what we did for the previous problem, except that we have a little bit more degrees of freedom. Okay, so let's do vertical force balance. So vertical force balance. Oh yeah, I need a coordinate system. So let's make a coordinate system. X, Y, and Z. We'll pick the coordinate system just like we had for the last problem. So vertical force balance is in the Y direction. So, so one thing to keep in mind when we do these problems is, like, I'm drawing these vectors, like this vector in this direction, but it's a vector. If I do it with respect to this coordinate system, this is in the minus X direction. And so even though I've drawn it to the left, I'm taking into account its sign when I write its components in this coordinate system. So, so this and this, so this is applied at the moment at the, so vertical force balance, we on the ladder. So this is on the ladder. So I have mg down, so it's minus mg with the big mg from the guy walking up the ladder. Then we have the center of mass. We have the weight of gravity on the ladder itself, minus mg. And then we have this up. We don't have anything for this because it's only a normal force. And so we have plus fgn. And this has to be 0. So this is all in the y direction because it's vertical force balance. Okay, good. So now we can actually write a condition. So let's save this up here. Fgn is equal to m plus m times d. So we have a condition on that. So now let's do horizontal force balance. Horizontal force balance. So this is in the x direction. So that's in the x. So I can write Fx. So the horizontal forces on the ladder is the friction force and the wall normal force. And so I have to add both of them. So it's the friction force from the ground plus the normal force from the wall. And these have to be 0. So even though they're drawn, this one's negative and this one's positive, because I'm keeping track of the vector, the signs and the vectors, this condition has 2 positive signs. So let's write that up here. Fg friction plus F n wall normal is equal to 0. That's the horizontal force condition. Now we get the interesting ones, and that's the torque balance condition. Okay, so let's compute the torque here. Torque from the ground on that point. We could choose to compute it up here. So how many nodes and unknowns do we have? Well, so we have 1, 2, 3. So we kind of need 3 equations. We've already got two, so one torque equation will help us, will essentially let us solve the problem. And we could compute it up here or here, it's not gonna matter actually, so, but I'm just gonna compute it, the torque at that location. So torque G, it's a vector. And what am I forgetting? I kind of, so we have a lot of terms here. So let's take, let's start with the torque from this guy and gravity. So what's R to this point? So let's do the first term from M. So R, which is the radial vector from here, is going to, so it has a distance a over 2 with a minus sign x hat plus h over 2 y hat. And the force is gravity, so the force is minus mg y hat. So when I take r cross f, the y hats will annihilate each other, so I really only care about these two. So I have minus a over 2 x hat cross minus m g y hat. And that's the first term. So now what about the second one? And the second one is at this distance a over 3. And so it's a over 3 x hat cross minus mg y hat. Following the same procedure, and again, because the gravity force is vertical, I don't care about the height of where that force is applied. So remember, this is applied at the center of mass when we compute torques on extended bodies, was computed at the center of mass point. So that's this part. So here we can ignore these two things because they have no radial distance, the radial vector is 0, so there's no torques for these two computing about that point. But there is one on this, from the wall normal force. So let's figure out what the radial vector is. So it's got a minus a x hat plus h y hat. And the force is horizontal, so it's FWN x hat. In this case, we don't care about this, but we do care about that. So we can ignore this. And so I add in h y hat cross f wall and x hat. There. Okay, so now let's evaluate this. So it's going to be mga over 2, so we have a minus and a minus with x cross y is z hat. So all the signs are positive. And now we have a minus and minus x cross y is z hat again. So I have mga over 3. And so let's just take these times, not x hat, z hat. So these are both positive, but y hat cross x hat is minus z hat. So it's minus h f w n z hat. And this has to all equal 0 for torque balance. Okay, so now then this, I can replace this with that and now solve for f g friction. And so let's do that. Fg friction will look like this, m over 3 plus m over 2. Oops, the minus sign goes outside everything. Times Ga over h. Yeah, that's it. Okay. And good. And I already have, okay, so let's write this condition up here. G friction is equal to minus m over 3 plus m over 2 GA over H. Okay, so, and this is a minus because it's to the left with this choice of coordinate system. Okay, so we've got the two components of the force exerted by the floor or the ground on this point of the ladder. And so I can take the ratio of the friction force to the normal force. So let's do that. So the friction force to the normal force, ground, so this is for the ground normal force. I'm going to take the absolute value of that because I don't really care about the sign of this. And so it's just this divided by that is m over 3 plus m over 2 GA over H divided, the g's are going to cancel, m plus m g, so let's just get rid of the g's. Okay, so this is the ratio of the friction force to the normal force. And so static friction, this can be at most the static friction coefficient. So in order to keep the ladder from slipping, this has to be less than the static friction coefficient. So mu s is the static friction coefficient. Coefficients. There we go. There. So yeah, so I wrote this problem with this is A and that's H, but we could have written H in terms of the length of the ladder and the once you've got A and the length of the ladder, you can figure out L. We can also describe it in terms of the length of the ladder and some angle theta. So this A over H is related to the angle. And so the requirement on friction, if you tilt the ladder over, A gets bigger and H gets smaller, and so then this required friction, the friction force would obviously be large. You need a larger friction force to keep it from slipping. So what if the so obviously it's like intuitively, right? If you put the ladder up steeply, it's a steep angle, or in this case, it's a larger angle, but it's more vertical, it's less likely to slip. So that is consistent with this setting. So what if we changed, I have a mistake here I have the mistakes in the 2's and the 3's. I have them backwards. So let's put them back the way they're supposed to be, because the center of mass is a third of the way up, and in this particular problem, we have the guy walking up is halfway up. All right, so now let's take the situation where the guy is actually walking up the ladder. And so these factors, this is where the center of mass of the ladder is with respect to this end. What fraction of the distance is he up the ladder? And this 2 right here is halfway up the ladder. But I could replace this equation. So supposing I have some fraction of the distance climbed. So this is how, if alpha is 0, if he's at the bottom of the ladder, and alpha is 1, if he's at the top of the ladder, then this equation would just get an alpha here. And if the center of mass of the ladder is in the center, this would be a 2 here. And so I can move the center of mass to be more appropriately placed. But when you look at this equation, if alpha gets bigger, then this ratio again is larger, and you need a larger friction coefficient to keep it from slipping. And so in other words, the required friction force increases as you climb the ladder. And that's why in the demonstration, when I got about halfway up the ladder, it slipped. So it didn't slip when I was at the bottom because alpha was small, but it slipped when I got halfway up the ladder. So that lets you figure out what happens when you change the distances. Okay, so far so good. Okay, so let's move on to rotational stability. In any case, so actually before we move on, just look at this problem a little bit, just one more moment. So I computed the torque around here, but we could have solved this problem by computing the torque around that point too. So when you're doing these problems, you may, so for here we had two equations for static force balance, for the force balance, and then we used one torque, but we had three unknowns, so three equations, three unknowns. We could have written down the fourth equation and it would have been redundant, but when you write down the fourth equation, computing torque around, say, around this point instead of around that point, sometimes it's easier to solve. And so, I would encourage you to just keep in mind that you'll get redundant equations. So you may be able to write down more equations than you have unknowns, but they're not going to give you any more information necessarily. Just something to keep in mind when you're trying to solve these problems. In this one, so remember we had two directions for the forces. Torques were only allowed, in this direction. So we only had one direction of torque to keep track of. Okay, so moving on to rotational stability. Okay, rotational stability. So this particular setting, we've got some mass, and there's a pivot point. So this is the pivot, but there's a different position for the center mass. So I can draw a vector x center mass. And so this is the compound pendulum setting. So the question is, what condition lets this be in equilibrium so it won't move? And I think last lecture I showed that if you integrate up the torque over the whole body, it's the same thing as applying the torque at the center of mass location, using the vector to the center of mass and the direction of gravity. So the torque is x center mass, and then this is mg, where g is the vertical vector pointing length, the gravitational acceleration pointing down, and this is cross mg like this. So the condition for torque balance or no rotation is this is 0, and that's equivalent to saying x center mass cross g is equal to 0, and that's also equivalent to cross g hat equals 0. Doesn't really matter. And I could actually consider the center of mass vector as a unit vector too. So what's this mean? This means that the center of mass vector has to be parallel to gravity in order for there to be no torque on this body. And if there were a torque, it would start to rotate, so it wouldn't be in equilibrium. So and if it's parallel, then the cross product gives us 0. So that's, equivalent statement. So there's two ways to have this condition satisfied. One is if you put the center of mass up directly above the pivot point. So if I have my pivot point, then I can put, to make it parallel, I have to have it directly above or directly below. There's no other way to make it parallel to gravity. So both of these would give us equilibrium points where there's no torque. One of these gives you a stable equilibrium point in the sense that, I perturb it very slightly and it will push back and come back to where it was. The other one, when it's upside down, it's unstable. And that means if I perturb it very, very slightly, then the force on it is away from the equilibrium point. So, so we could think about this in terms of potential energy. So if I have, so let's now think about, so potential energy for compound pendulum depends on mgz, where z is the distance of the center of mass position from the pivot point or from any other location. So, so I could think about this in terms of potential energy. So let's write a potential energy. So this is U, maybe of z, and this is Z. And let's consider what happens at some, so I'm going to call, not XZ, so we'll call this Z star. And this is the equilibrium point. Equilibrium. Okay, so what do I mean by equilibrium? That means no force. So remember, force is the gradient of the potential. So F is minus du, in this case Z, where Z is the height of the center mass. And at equilibrium, this is 0, and so the derivative is 0, and that's another way of saying it's a local minimum. So du dz evaluated at this equilibrium point is equal to 0 at equilibrium. So if I draw on this so that it's a minimum in the potential energy, which makes sense if I have my pendulum and I let it tilt down to the bottom, the center mass is as low as it can be. And so the potential energy is as low as it can be. But then, so this has a positive slope on this side. So the force is now the opposite, minus du dz. So the force is back in this direction. So it restores. And here we have a negative slope, but the force is the opposite sign. So it's back that way, it restores. So this is a stable equilibrium point. And that's equivalent to the, the rotating, the compound pendulum being down at the bottom. We can just reverse this whole problem and look at unstable equilibrium, which is going to look exactly the same, except now we've got the center of mass up on the top. And this is still an equilibrium point. Z, so this is Z star, this is U of Z. This is still an equilibrium point, but now this is negative slope, so the force is in the opposite, so it's that direction. This is a positive slope, and the force is now in that direction. So if I take the pendulum and I tilt it very slightly over, it forces it away from the equilibrium point. And this is an unstable equilibrium. Okay, so we could actually now, looking at this potential energy curve, classify these equilibrium points just based on the second derivative. So if the second derivative is positive, then we have a stable one, and if it's negative, then you get a curve this way, and it's unstable. So we could think about the problem that way too. Okay, good. So because I started drawing potential energy curves, it's a good time to start thinking about, so we're going to take a step further now and not just talk about equilibrium conditions, but we'll look at near equilibrium positions. Again, using these like one-dimensional examples. So let's see that. Harmonics of motion. So let's talk about motion near a stable Okay, so yeah, so let's do that. So I'm going to talk about potential in a single dimension. Small break, now we're back. Okay, so where was I? We're going to talk about motion near a stable equilibrium point. So I drew an arbitrary potential here, and we have two potential wells, and the bottoms of these have zero slope. And so here's an equilibrium point. x, which we'll label x star. And the important point here is that we're talking about motion near a stable equilibrium point. And so we're interested in what happens when a particle has energy down here and is near this particular position. So that means we can use a Taylor series. So that's when you expand a function near a particular point. So do that. Taylor series. So to remind you what Taylor series look like, if I take ux and I expand it near any particular point, in this case I'll write down x star, plus then I take the first derivative and I evaluate it at x equals x star, and then times the first order term, which is the distance to x star, plus the second derivative, again evaluated at the point that we're expanding around, and now we have the quadratic term divided by 2. So that's the Taylor series to second order, and we could expand it out to higher order if we want. So our condition for x star being an equilibrium point is this. That the derivative vanishes at that point. Otherwise, it wouldn't be an equilibrium point because this gives us the force. So, so that's convenient. This goes to 0 near the equilibrium point. So I can define something new. This is a constant. It's not dependent upon position. So I could write the potential near the equilibrium point to look like this: 1/2 k x minus x star squared, where I define k as the second derivative evaluated at the equilibrium point. So look at the form of this. It's a constant plus a quadratic term. So really what we've done by assuming that we have a second order expansion is that we, put a parabola that hugs the curve and goes through the equilibrium point. So it's like we're only taking into account the quadratic part of the curve. We could, you would get a closer approximation if you took it to, cubic and quartic terms as a function of distance away from the equilibrium point. Okay, so what's the motion? So remember, let's talk about motion near an equilibrium point. So, so if I have a mass m, and I want to know what's the motion like near this equilibrium point, then I can have mx double dot is equal to minus du dx. It might be convenient for us to transfer coordinate systems. So let's define x minus x star to be some new variable y. And I can take the first derivative of this. So if I do this coordinate transformation, my equilibrium condition doesn't change, but I can also do this. And I can also do du dx is equal to du dy, because they're only different by a constant, so it won't really make any difference. So since I can do that, I can take the equation of motion and rewrite it to look like this: y double dot is equal to minus du dy divided by mass. So so now let's go down to our Taylor series expansions. U of y is a constant plus 1/2 ky squared from this. And when I take the derivative of u with respect to y, the constant goes away. Du dy is equal to ky. And then this equation becomes y double dot is equal to minus k over m y. And so you should be able to recognize that as the equation of motion for harmonic oscillator with frequency square root of k over half, like that. Only k now is actually, remember what we defined k as. K is the second derivative of the potential energy term evaluated at the equilibrium point. So this is the frequency of oscillations at the bottom of the potential well, and that's what the motion near a stable equilibrium point is like if you're in a situation where you're at the bottom of the potential well. So you can ask, well, what does it look like if you're on an equilibrium point where you're at the top? You know, you flip it upside down, like the pendulum, instead of being at the bottom of the pendulum, you turn the pendulum upside down, it's unstable. Well, then that minus sign turns into a positive term, and the solutions are exponential divergence away from the equilibrium point. And so if you're interested in, like, for example, the control problem of how to keep an upside down pendulum stable, then that time scale would be relevant for, you know, for how fast you need to be able to push it in order to keep it from falling over. So in any case, so that's with the sign flipped, that would be motion near an unstable equilibrium point, and this is motion near a stable equilibrium point. Okay, good. All right, so so we just figured out how to take the shape, the second derivative of the potential near a stable equilibrium point to figure out the frequency of oscillations. And so I thought I'd give an application of this in the setting of celestial mechanics. And so the application is going to be radial epicyclic motion. So what do I mean by radial epicyclic motion? So so one way to think about Keplerian motion, so is you can think about motion in a circular orbit. Radial epicycles are oscillations in radius around the circular orbit. So so supposing we think about you know, put the sun here, and we have a planet, and there's a circular orbit of a planet going around the sun. Well, so now let's perturb that orbit very slightly. We'll start it a little bit off. And we can look at an eccentric orbit that's near the circular orbit. And so we can think about that orbit as going out in radius and then coming, so here's apocenter and here's pericenter, or aphelion, perihelion. And so you think about this orbit as going radially in and then radially out. And that's equivalent to thinking about it as being an ellipse. And so if I plotted like radius as a function of time, the circular orbit would be flat, but the epicyclic orbit would do this in a period. For the Keplerian orbit, the orbit actually comes exactly back to where it starts. It's an actual ellipse. And that's another way of saying that radial oscillation period is the same as the orbital period. But when you don't have a Keplerian setting, like, so an example, even in the solar system, the planets cause perturbations, and it's not exactly Keplerian. And so what happens is the orbit doesn't quite come back. So the frequency of the radial oscillations is slightly off from the orbital rotation period. And then the orbit doesn't quite come back, and so it slowly tilts. And so you can think about the angle of perihelion. The perihelion location shifts very slightly each orbit. And one way to talk about that is a precession of the angle of perihelion. So in Keplerian, so near Keplerian settings, those precession rates are really slow. Precession periods are tens of thousands of years for the planets in the solar system. So it's a very good approximation to think about them as ellipses, actually. So in the galaxy, however, the potential is really different than the Keplerian potential, and the orbits really don't close. So they actually do things like this. They form what's called a rosette. Yeah, so the epicyclic frequency is quite different than the angular rotation rate in the circular orbit. Okay, so why is this an application of motion near a stable equilibrium point? So I'm going to go back to something that in the previous set of lecture notes where we talked about angular momentum, orbital angular momentum, about the object. So consider a planet in orbit around the sun and compute the angular momentum with respect to the position of the sun, which you assume is fixed. And that's a conserved quantity because the force is radial, only in the radial direction. So remember how we had done that? So we took the energy per unit mass. Mass is 1/2 v squared plus the potential energy, which is a function of r. And we expanded this to the radial component of velocity plus the tangential component of velocity. And then the tangential component of velocity is just the angular momentum divided by radius. So this is L squared over 2r squared. R, and this is potential energy per unit mass to be consistent with this. And then we took this and we called this an effective potential. So all the radial information, so once you choose the angular momentum, this is only dependent upon radius. And so the equation of motion in the radial direction looks like this. That's not what I want to do. I want to do d, let's call, let's call the position, the radial position A or something. dr squared is equal, this is what I mean, dr dt squared. It's the acceleration. So we would have forces equal to mass, force is equal to mass times acceleration. So because we're doing everything per unit mass, the acceleration in the radial direction looks like this, ddr of the effective potential. And this is an r here. Okay. So this is the kinetic energy taking into account only the r dot parts. This is actually r dot squared. And this is the effective potential energy that's a function of r. And this is the equation of motion. Okay, good. So let's write that down a little bit more carefully. So we've got U effective is equal to 1/2 L squared over r squared plus the potential energy. And if it's a Keplerian situation, it's L squared over 2r squared minus gm over r. So that's the potential energy per unit mass, where this is like the mass of the central body. Okay, so let's just to remind you what the shape of this this effective potential energy function looks like. So gm over r looks like that, and this is r, and So this would be without the angular momentum component. But this thing goes to positive infinity as r goes to 0. So this thing is up here. And when you add them together, you get a function that looks like that. And so there's, at the bottom of that is where you have a circular orbit. So this is, so once you choose the angular momentum, r star is a circular orbit. And it's in, when you draw it like this, it's also an equilibrium point in radius because the radius doesn't change in the orbit. So it's an equilibrium point also. And that means we can use r star, which is the radius of a circular orbit with angular momentum L. You have to choose L first. And you can look at what's the oscillation back and forth around that circular orbit. And those are the radial epicycles. So those are the, like, the speed, the epicyclic motion is like the frequencies, how fast they, what the frequency of those radial oscillations are. So, so we can take our effective potential here and take its second derivative, and that will give us the this effective like spring constant thing that is related to the epicyclic frequency. So let's do that to d. So du effective dr. So I need to take the first derivative first. And that's minus L squared, so over 2r cubed. And there's a 2, the 2 cancels out. And then I have plus gm over r squared, and that plus. And if I set this to be 0, set equals 0, and I can find r star, which is the equilibrium point. And actually, so let's do that. So we get L squared is equal to gm so r star. That's actually the condition for this in terms of the angular momentum. Now we need to take the second derivative. So let's write that. Let's save this somewhere. Gm L squared, that's the other way around. L squared over gm. Now let's take the second derivative. D squared u effective dr squared is equal to, I need minus plus L squared times 3 over r to the 4th minus 2 gm over r cubed there. And this, we set it to be our spring constant. Let's just call it K. I'm going to call it K. That's our spring constant. We need to evaluate this in order for it to be our spring constant. So if I evaluated at r star, now I get my spring constant. Okay. And yeah, so then, so what's the frequency then? So so when we wrote the potential like this, it's equal some constant plus 1/2 K. In this case, it's going to be R minus R star. Where K is that thing, d squared, the effective potential, dr squared evaluated at r star, which is the radius of the circular orbit with angular momentum L. So, as is commonly done in celestial mechanics, instead of writing potential energy, usually work with potential energy per unit mass, actually. So this is actually potential energy per unit mass. And so this is actually K divided by M. And so this thing is actually, it's not, so remember normally you have the frequency of oscillation is square root of a spring constant divided by m. But actually, in this particular case, we've already divided the spring constant out. And so this thing, this k that we did here, is actually the square of the oscillation frequency. So we can write this down as omega squared, where this thing is the epicyclic, omega is now the epicyclic frequency. So that's why this, well, so this expression is in fact the epicyclic frequency. And if you insert R star is equal to L squared over GM, what you find out is that you get the the square of the angular rotation rate for in the Keplerian setting, the epicyclic frequency is equal to the angular rotation rate for the entire orbit. So in more general situations, so this thing here, this is this, so if you write the effective potential, you don't necessarily have to put in Gm over R here. So this is the first derivative of the potential without the angular momentum, and the second derivative of the potential. So if you had a particular potential, you could evaluate the epicyclic frequency for that setting. And so for the galactic setting, an approximation that people like to use for rotation in the galaxy are logarithmic potentials. And then if you do that, you wind up with these two terms looking quite similar, and you wind up with epicyclic frequencies the square root of 2 times the angular rotation rate. So the actual value you get depends on the radial form of the potential in the original system. But in any case, that's an example of looking at the motion near a stable equilibrium point. So there's no reason why we can't think of elliptical orbits as small radial oscillations around a circular orbit. Okay, so that's that part of this example. So the last thing I wanted to talk about is blocks. So stability. And stacks. Blocks. Okay, so the problem I want to talk about, so let's just do 2 blocks. Here are 2 blocks, and the question is, I can move this block on top of that block, and when is it going to fall over and start to tilt? So the relevant point to think about is this point. And really we want to think about the torque from this block computed around this as a pivot. And so if the torque is this way, then the block will be held up by this other block. But if the torque is in that direction, then it just pivots around this point, it falls over. And so really all we need to do is compute the torque around this pivot point, and we'll know whether the block either is stable and gonna stay happily perched there, or whether it's just gonna fall over. So, so just like our compound pendulum, we just figure out where the center of mass is of this block. And if the center of mass position is to the left, so when we have to exert mg, so it's r cross mg. So the relevant part of the radial vector is only the horizontal component. And if the horizontal component is in this direction, then r cross f gives a rotation in that direction. So we only care about whether it's the horizontal component to the center of mass is negative or positive with respect to this point. So if the center mass of this block, of the top block, is to the right of the left top corner of the bottom block, then it's stable. It took to the right. Then it's stable. So that's the criteria. So we're being pretty careful what we're computing here. The center mass of the top block and its position with respect to the left corner of the bottom block. So that's the main thing that we need to think about. So this is a torque balance condition, right? So this is a you can't have a torque on the block. If there's a torque on the block, then it starts to rotate, and then it falls over. Okay, so this is two blocks. So let's move it over a little bit and make it just barely stable. So if we say each block is length L, so I'll just make it a little bit like this. So each block is of length L. To make it just barely stable, the center mass distance from this point would be L over 2. So that's L over 2 for the critical stable line. So now what I want to do is compute the horizontal distance with respect to the center mass position of this block. So why am I doing this? Well, I'm doing this because I'm going to put another block under here, and then I'm going to ask, will the whole thing tilt over or not? So I'm going to try and put another block, raise this, and stick another block on it. So in order to do that, I need to know the center mass position of both of those two blocks. So I know these guys are stable, and then I want to perch them on something else, and I want it to still be stable. So that's what I'm going to calculate now. So so the center mass position, so this one is L over 2 over. So I'm going to compute the center mass from here. So it's L over 2 for the center mass position of this one. And this one, since I'm at that position, it's 0. But I have 2 blocks, so I divide by 2. And so this is equal to L over 4. And so that means this distance. So here's the center mass of both of these blocks. Is L over 4 away from the center of mass position. And now, so that's the center mass of those top 2. I want to know what the overlap is. So it's L over 2 minus L over 4 is L over 4. L over 4. And that means I can put this block underneath like this and have the overlap is L over 4, and now it will be critically stable, like right at the critical. Okay, now I'm going to repeat myself, and we're going to take the center mass of the third block, and we're going to compute the center mass of all 3 with respect to that point. And so it's going to be L over 2 plus L over 4. That tells me how far between here and here is, so that's this one, plus L over 4, which tells me how far away this center mass of that guy is, plus 0. But now I need to divide by 3 blocks because I have 3 blocks in my computation. So 1/2 plus 1/4 plus 1/4 is 1. And so this is equal to L over 3. And so the center mass of all 3 blocks from the center mass of this one is L over 3. And that means this is this distance is L over 2 minus L over 3, which is equal to L over 6, right? Actually, it does a little bit. L over 3, and this is L over 6. So this is the position of the center mass well, 3 blocks from that point. So that means I can put another block under like that. And the overlap is L/6 for stability. So you can keep doing this, and you can get the pattern where you keep consecutively adding the distances. And there's you can do this iteratively. This is L/8, and then you get L/10, L/10, et cetera, et cetera, et cetera. Is that correct? Yeah, that's right. So you can ask, is there a limit to the span that you can, like if you're building a bridge, is there a limit to the span? And there isn't. You can as long as you're willing to keep piling blocks on, you can make a really big bridge. And it doesn't necessarily need to be hugely massive, because you can make these really thin if you want. It doesn't mean anybody can walk on it very easily, but in any case, you can make a really big, you can make it really extend really far without it falling over if you want to. So one thing to mention is for this particular problem, I assumed all the blocks are uniform density. So if you want to fool with people's intuition, you could drill holes in blocks or add weights and make them balance in unexpected ways, because the relevant thing is the center of mass position. It always has to be in this case, to the right of the pivot point that would let it fall over. So that can be fun. Maybe you can design blocks that defy people's intuition by embedding weights in them, for example, not having uniform mass densities. Okay, so I think I've covered what I meant to have covered during the portion of the lecture that I forgot to record. So this should be recorded, and so we're set. So I guess I'll stop there and then sign off. See everybody on Thursday.